And so we can move to the final part, which is a panel discussion. Just see if I can. Okay, so I'm seeing you all. The panel members will be Marcus and Laura, who are already introduced. And so, as I mentioned, Dana will also join. And just a short introduction for Dana. So Dana Kulic is a professor at Faculty of Engineering at Monash University in Melbourne, Australia, and she joined the university in 2019. She is also the director of the robotics research group at Monash and is leading the development of new robotics precinct at Monash. Dana is an expert in human motion analysis and human-robot interaction and pioneered systems to quantify and control safety during human-robot interaction based on both human and robot perception. And the last panel member is Jennifer McGinley. Jennifer, can you just wave so that everyone sees you? Jennifer is a professor of physiotherapy at the University of Melbourne. She was previously director of the Center for Clinical Research Excellence in Clinical Gait Analysis and Gait Rehabilitation in Melbourne. Jenny has clinical physiotherapy expertise in the field of neurological rehabilitation and particular interest in clinical interpretation of three-dimensional gait analysis data and issues relating to data quality. So the way we imagined this was that we start by asking a couple of questions, and then the audience can take over. And if you have any questions, so I'll start with the first one. So as we already discussed today, clinicians have been the ones driving the physical therapy and delivering physical therapy, and also as seen today in all these talks, there are many technologies around up and coming that can complement but also advance physical therapy and likely to the level not even comprehensible today. And so my first question is, and I would ask this first to non-clinicians, so Dana, Marcus, and Laura, either of you or all three of you, and then also Jenny, what is or should be the role of clinicians in the development of computational models and robot-assisted gait therapy as a kind of blanket term, and how can we actually utilize the vast knowledge that clinicians actually possess and that is not necessarily or not often quantified and reported in the literature? You can take it, whoever. If we can start first with a non-clinician. What do we expect from clinician in that sense, and then if we could hear also from Jenny.
Maybe can I start?
Sure.
Actually, we work very closely with clinicians, right? So I'm actually part of the hospital, and I don't think that we could do anything without clinicians. that's everything that we do, it's irrelevant unless you are yourself also a clinician. And you can see this, right? So there is this well-known review about the hand rehabilitation robots. And it was a huge review with many, many different inventions. And it was said that only less than 30% of these devices actually made it into the clinic. And even less has been commercialized, right? And then the question is, why is it? And it's because we are engineers, we always want to have very sophisticated, many degrees of freedom robotic devices, right? This is how we were educated. But then you go with your robotic devices that you just created inside of your lab, go to the clinics, and then they said, well, I need 30 minutes to put a person in here, and 30 minutes is only the time that I have to do rehabilitation, right? So for me, the way to go is the co-creation of technology from the beginning, together with the clinicians. So in group, right? Not only reach the clinicians to get patients for your experiment, because you are the ones who are having the experience. That's my way of thinking it.
Thank you. Dana, Marcus, do you have anything to add or?
I think clinicians can play an important role in both the development and testing of models. In terms of the development, an example that I can give that is current in my lab is we're trying to develop a model that includes a more detailed representation of the torso musculature. And I think that this is, and use a model like that in to study activities such as jumping and running. So, you know, why would we want to do that? To study potential interactions that may be occurring between the lower limb muscles and the core muscles of the abdomen and back. And so we are working very closely with an anatomist and a clinician in order to identify the appropriate muscles. How can we best develop a model striking the compromise between simplicity, if that's the appropriate word here, and functionality. You know, we want to incorporate the key muscles that capture the function that we want to study, but also we don't want to include indiscriminately muscles that we don't need to, because we want to keep computational time down. So that's an important role that people with clinical training can play. In terms of testing models, you know, I think that this is a very important part of the computational area as well. I think ultimately it would be great. In a talk earlier today, I think we saw an example of actually clinicians using models, the talk that Antoine gave. So I don't know how realistic that is to expect clinicians to actually use models, but there are those who are very interested and have the time and perhaps even some of the technical background to be able to do that. So I think that that's a potentially very important role to play. Okay, I'll stop there. I think Heike has her hand up.
Question to you, if I may.
Yes.
So what do you think, is there a need to have more people who have both types of education, or sort of mixed education, like technical medicine, which is something that we now have at TU Delft? So people have knowledge of both fields, but they are not necessarily as deep specialists in either field. Do you think we need more of these people, or do you think we need better communication between the single specialists?
No, I think that you know, in other branches of science, it's very common to have an MD, PhD. And there are programs that you can take where you have dual training. And I think that is predominant in fields like in the life sciences, you know, biochemistry, molecular biology, where people who have a medical degree go on to then do some training in the life sciences and have a lot of impact and become research clinical scientists and have a lot of impact.
Just do both educations as consecutively, which means that you spend more time, as opposed to a program that's as short as either of the two individual programs and tries to mix them.
Yeah. Well, yeah, that's a difficult question to answer, because I think that you want to be careful about not being trained in either discipline adequately in that case. So yeah, I think I guess being trained deeply in both science and medicine, you need to make that commitment. It's a big commitment, and I think the commitment ultimately is probably made to research rather than practice. But that's just my view of things. But yes, you know, and so if we can't do that, then we need to find ways, obviously, of working very close together. Yeah, sometimes the geographical separation is a barrier to that. So that can be overcome by embedding clinical people in the same department as technical people. We tried to do that in my former institution, and it worked very well. We brought clinicians from the Texas Health Science Center, which is the largest medical center in the world, into the Department of Biomedical Engineering in Austin. So, you know, they had dual appointments. The people in Houston had dual appointments in Austin. And so faculty in engineering, they spent, you know, sometimes 1.5 days in the department, and sometimes they even had lab space. And that seemed to work really well.
Thank you. Jenny, did you want to give a clinical perspective?
Yes, thanks. I'm clearly going to say, I think that the relationship, I think, as everyone has been expressing, is really important between clinicians and other members of the team in this space. And I think we've probably all historically seen, you know, perhaps projects connecting between the clinical world and the robotics or engineering world a bit too late, and perhaps products not missing the mark. So I think we can all, you know, see significant advantages to having that. I think we can think also about, as Marcus said, what the barriers are. So I think that while clinicians will be predominantly clinical, researchers, scientists will be, we need that core interdisciplinary team who speak common language together and can understand a little bit more of each other's. And I'm looking at Scott here, who has, you know, a physio degree, a biomed degree, and a PhD that's looking more at more complex biomechanical modelling and thinking about how we do that. I think joint supervision of PhD students is something, it might be some way that we can go towards that. We're hoping to see more clinician researcher scientists within our field in Australia, but it's a difficult thing to see. I think from our own point as clinicians, you know, some of these talks have incredibly resonated in themes such as managing error. The physical human interaction is very much the epitome of what we do in clinical practice. If you recall that early video of Gavin and a colleague walking someone, we're essentially having a hands-on interaction that is dynamic and changing. It's allowing error. It's sometimes resisting, it's sometimes correcting, it's alternating from different joints. And I think we can think more about what it is we're doing when we see people learning in movement, and what it is we'd like to replicate in a robotic device that we can use in that training period where we're looking towards restoration of normal movement. So to be thinking about what it is that we're doing and perhaps having conversations about that. The notion of error and motor learning is intrinsic to what we're doing, and we want movement, even though we might be training straight line walking, we want it to be variable. We want errors to be random. We want errors to vary in magnitude and direction. If we look at a harness, we want lateral veering. You know, we want the person to have the ability to explore space, get meaningful feedback, so somatic feedback. But we're kind of somehow regulating that by how much assistance and direction we provide. And we probably need to be more reflective about that in order to be able to speak to you about what we think might be important as well, or what our experience would lend. So I see enormous benefits, you know, that this meeting, these conversations are really useful, I think. But also thinking about how we can connect often our language is different. You know, often different fields would use different terms. So I think that might be a point of view as well.
Yeah, I think we all experienced this where we think we're on the same page, but then at some point we're like, oh, that's not what you mean. Anyone else wants to add to this? Yeah, we have a question here. Sure, go ahead. Can you just take the mask off so we can actually?
I mean, I have a comment on the
Sure.
working together. I don't think you need double degrees. I don't need to talk too much. So this will be a bit controversial. I think what we need is for us on the biomechanics side or on the robotic side, make a proper abstraction of what we're doing. For example, okay, you see this phone, this is a huge computer science behind it. Yet every one of us is using, because it's a nice abstraction of that very complex thing. And if we can make an abstraction of biomechanical model so that the clinician can easily understand it, easily use it, then it will be easy for them to actually apply. So far, I mean, OpenSim is quite a nice interface and everything, but yet it's still difficult to use. Even for me at the beginning as a roboticist, it was very difficult to use. And if we make some abstraction of this, for example, we are working together with Azure. He was one of the principal developer of OpenSim. We're trying to make an abstraction of, for example, a rotator cuff muscle into a simple 2D plane. We call it spray map. So you can actually see a dot moving, so like kind of a straight face. And it's kind of like a hill and valleys. And you see where you are, you can see how dangerous it is in that space to repair the muscles and so on. And I think this is the way to go, kind of make the proper abstraction. And if I give you another example, an astronaut that flies the space shuttle, yes, it doesn't understand all the rockets in mind.
Thank you. Did you all hear the comment? Yep. More or less. So we need basically an abstraction. It will then be much easier for clinicians, for example, to use technology, just like you have a mobile phone. All of us are using mobile phone, but only few of us might understand what's actually going on, but that doesn't stop us from using the phone. Or another example was an astronaut that goes out in space and they don't really understand the rockets and whatnot, but that's not the point. They can still do their job. So we need something similar in this kind of to solve the problem between researchers versus clinicians. We need an abstraction of technology so that clinicians could use it. Is anyone?
I want to say something.
Sure, go ahead.
Because this is actually unidirectional communication, right? So basically what you want is the clinicians to understand what you're doing. And I think that it's a big error that we engineers don't understand clinicians. And this is the origin of everything and the lack of acceptance of our technology. So, yeah.
So if I can just, so what you're saying is it's in this scenario, it's the engineers that should understand more clinicians than clinicians should understand, well, not engineers, researchers.
It's bilateral. It's a communication between two people, right? So, and the information has to flow in both senses, not only from us trying to fit and make them use it. So let's gonna make it easy so they use it. No, it's what is the unmet clinical challenge? Listen to them. So one of the things that I do with my new PhD students, and usually they are all engineers, is I send them to the clinics. So they just spend at least 1 or 2 months in the clinic every day, and they talk to everybody. So not only into the occupational therapists, but also neuropsychologists, with everybody, right? And then they take notes and then they talk with everybody. And this is the way, right? Because you learn to listen, you need to understand, right? And then it's like you retrain your brain to be able to understand them. And this
Okay.
is for me the first step that has to be done.
Thank you. Any comments? No?
I mean, of course, this is a necessary step to make a right abstraction anyway. But again, in the end, it has to be an abstraction because if it's something too complicated, yeah. Like I said, even I almost gave up on biomechanical models because there were so difficulty.
Okay, so the point is basically, yeah, we do need abstraction. This is just the first step, but we do need abstraction. Danny, you raised hand.
Yeah. Thanks, Tomislav. I was just going to ask, or add, I guess, to the astronaut example. I guess the engineers who designed the rocket actually understood the problem of the astronauts. That was part of the missing part of the example, I guess, the analogy.
So you are throwing the ball into a researcher's court, saying you need to understand the.
No, it hasn't changed. It agrees with everything that has been said. It's just the analogy actually is fitting, except what we probably didn't realize that the engineers who designed the tools for the astronaut to be used in the outer space actually understood the problem, whereas often in our case, maybe we did not.
Yep.
Can I just make a quick point here? There is a potential third partner that we haven't talked about, and that is, and it's discipline specific, but in my particular discipline, industry is very important. And we're not just talking about engineers there. We are talking about engineers, but different engineers to myself, for example, who know a lot more about engineering per se, and in particular their product than I do. And so when I work, for example, in the orthopedic area, I have to work with orthopedic surgeons, implant manufacturers and their engineers, and then us. So, that's a three-way.
I think there's another group that we haven't talked about, and those are the actual users. And as we saw from Laura's talk, and I'm sure Jennifer can comment on this, like the motivation of a person to use this technology is significantly impact the actual success of that technology. And so thinking about the users and involving them in that co-creation process, I think, is really important.
Yeah, again, it can be discipline specific as well. For example, in orthopedics, patients basically do what the surgeon who's going to implant the prosthesis tell them.
Well, even in orthopedics, they may have to participate in a rehab program afterwards, which can significantly impact whether the surgical procedure is successful.
I think the principle we're all arriving at is having the relevant stakeholders engaged more closely from discovery through to industry. I know certainly clinicians can be intolerant of new devices because we don't understand where they are in the scheme of development. I know certainly, we also need to understand we can't look at something and go, oh, that's not going to work, because it's actually not meant to work right now. It's meant to be a proof of concept, or it's meant to be a point of discovery. But I think coming together much earlier and consistently thinking about who is the end user, who could use it, who else might be able to use it, engaging whoever the stakeholders are. Clinicians, I guess the other point that is important, that was touched on a little bit by Gavin at the beginning, we know that cost is going to be really important. Health costs are blowing out. We have aging. So cost is going to be an incredibly important sort of determinant at some point. It's quite costly to have 3 physios walking 1 patient. We don't like that. We know that from a learning point of view, people need lots of practice and lots of repetitions. We just want this, devices that allow us to use them in the way that we think the person needs. Yeah,
that's true. Okay, so we'll move to the next one. So we heard in several talks today about individualization and personalization, and this is not just in our field. This is now personalization seems to be a thing in many different fields. And we also know that personalization is changing the outcomes of both human-robot interaction, of computational modeling, of physical therapy. In the end, every patient is approached individually. But when we look at technologies, and most of these things that we do are short-term, we don't really do long-term studies where we could really see the effects of what we are doing in terms of technology. So how can we even know that what we are doing right now is the right way to go, and that what we are doing is actually capturing features that will kind of in a long run be the right features? How do we know that what we are kind of, the way we are individualizing using technology is actually going to have positive long-term effects? Who would like to take on this one? No comments, maybe from the clinical side, like how do we because when you do the therapy, you do assess the patient, and then you try and do something that you believe is the right way to do. But if we have technology that can predict potential outcomes, and then it gives us a specific way to go, how can we know that we can trust it?
I think an analogy that is close in some ways is the way that the motion capture data has transformed, for example, biomechanical and surgical management of children with cerebral palsy and their biomechanical alteration alignments. And so it's only through using technology that surgery is incredibly highly individualized. And quite a lot of different fields of biomechanics and muscle modeling have contributed to, I think, a good example of how we see technology transforming and measuring and reassessing and looking at the long term. We have the 5-year studies, 10-year studies now. So I think that field of knowledge, while not necessarily assistive devices, is an illustration of that really nice clinician modeling expertise. It makes sense that we see people individually. I think it's a matter of having systems built in that measures movement over time and change. So I guess that's a thought of mine about how it does connect the dots.
Thank you. Non-clinical side, anyone wants to comment?
I mean, you can only be sure about if something works when you try it, right? So basically, we need clinical trials in there, unfortunately. But maybe in this personalization, one of the problems is everything related to ethics, right? Because then you have a machine that it's making decisions about the future plan of the rehabilitation. And then it's very difficult to have this approved via ethical approval for obvious reasons. But I'm quite convinced about this explainable AI, so that actually you are providing recommendations rather than enforcing protocols, right? In a way that you can explain decision of the machine to the therapist, and then eventually the therapist is the last one who has the word to say, I accept this or I don't accept. That's another layer of ethics, right? And something to study, how much we trust this recommendation and how much we didn't, and how much the therapist feels like it's free of choosing when you have something that it's provided by a machine that you believe is smarter than you, right? But yeah, it's a difficult question, this one, huh?
But it's a very good point. That's a very good point.
If I can provide an example from my own field. So traditionally, the way they put implants into joints is by having different sizes. And so each patient gets a particular size that might be closest, that is said to be closest to fit their joint. But now what they're doing is using imaging to actually make the implant custom to that patient. And how do you, so it goes, I want to go to the question that Tomislav posed, and that is, how do we know we're on the right track? Well, in this particular case, it's ask the patient. And so, you know, there are patient-reported outcomes. They fill out these things. There are happiness factors. And there's a lot of data out there that shows that patients are generally more happy when they have these custom implants, and in particular, one type of design of, for example, knee implant that is stabilized on the medial side. They seem to perform much better. They have greater range of motion. They just are happier with them. So it's hard to argue once you've put the implant in. If the patient's happy, you would say that that's a successful outcome. So
yeah, that's also a good point. But I guess that might not always work. Like if you look at stroke patient, then we want to help them to relearn how to walk. There isn't much about whether they are happy or not. It's whether they can walk. Yes, sure. Whether they can move by themselves, it's an important thing. But it's, in this case, I guess it's more on the quantifiable, objective side rather than subjective. But yeah, of course, also the feeling that they have.
But just one comment following up from Laura's comment about trials. I mean, trials like that have happened in clinical gait labs with orthopedic surgeons, you know, one group having three-dimensional gait analysis data and one group not, and looking at the recommendations for surgery. So there have been clinical trials looking at decision-making through still humans looking at the biomechanical data, experienced humans, compared to not having that information. So I think it was LA Children's, they've done those, showing that the information is useful and of benefit. So it is, you know, if AI is making the decision again, you could actually test it.
Okay, thank you. Are there any questions? Because it's already 6 p.m. We should finish. Are there any questions from the room?
I have a provocative question to the clinicians or the physiotherapists. Let's assume we have now perfectly personalized.
Can I ask you just to come here so I don't need to repeat, and so they can directly hear you?
Hey. So yeah, it will be a little bit of a provocative question to clinicians and physiotherapists. Let's assume we have now perfectly personalized models that the robot can use and perfect robots that can do everything themselves. Would you be prepared to actually change the nature of your job, because the robot can get measurements, quantitative data, can have the insight through the model? Would you be willing to actually then change the nature of your work? Because probably then your role would be more a supervisor rather than the doer.
I don't know what Scott thinks. Yes, in a heartbeat. You know, it's not so much what my hands are doing, it's what my mind is doing. So choosing when you would use it, who you would use it for, what you would get it to do. We want to be able to tweak to an extent, to have some ability to change the parameters. And that's really because people with stroke change quickly over time. So they're not going to be the same over time in the early stages. But we have lots of other things to do. So in an ideal world, if I could program something to do what I think is reasonable, a reasonable approximation of the practice they need at this point in time of their journey, yes. Scott, do you agree?
I agree with Jenny. So I'm a musculoskeletal physio, not a neurological. And yeah, we will see patients in 15 to 20-minute blocks. And if there are faster ways to evaluate someone for a biomechanical outcome, I'm more than happy to do it. I'm not sure if it's going to encompass the whole session that we do in terms of treatment. There's a lot of different things we do. Got to consider interaction with the patient and the issues that they have as well. You know, there's a lot of complications there that we need to manage, whether it's a work cover patient or, you know, a kid with a knee pain or an 80-year-old. So it's all personalised, if that makes sense.
Thank you. Okay, so then we need to finish. So if I can just have one more. So seeing as where we are going now with the technology, with robotic technology, computational modeling and so on, what would you say is the next big breakthrough, or would you like to see in bringing a physical therapy as done today, and with all these new technologies, what would you like to see as the next big breakthrough? Or you think it's the necessary next step before we can actually really start using this on a widespread scale? No, you don't have any wishes. I guess
that's a question to the physical therapist. Is that right?
Is it a question to all of us, or?
It's the question. I mean, we are all working together and we all have the same goal ultimately, right? Help the patient. So yes, the technology is maybe in that sense going to change much more what clinicians do than us researchers, but at the end of the day, we want to do the same thing. So I guess we should want to the same or similar. So question to everyone.
Well, I mean, if I can just quickly answer it from my point of view, I think what we really need that would change a lot is more accurate measurements of everything, but in particular, muscle force. If we can measure muscle force non-invasively, then I'm happy to not ever develop another model ever again, because that's the answer.
Okay.
But you know, things like that is what is the holy grail, I think. And it's not going to happen. It's not going to happen in my lifetime, but hopefully the next generation or the generation after that will find a way to do that. And
we've heard similar in ICOR. There was a question on the next big breakthrough in prosthetics, and the answer, two answers were not in our lifetime. One answer was not in the lifetime of my children. So yeah, let's hope that we can speed up the development.
It wasn't meant to be a pessimistic comment, just realistic.
No, yeah, I know. Scott, you wanted to ask or say something?
Yep. I have a great interest in biofeedback moving forwards. I see a great deal of variation, whether it's in response to an intervention biomechanically or just variation between sessions in motion capture. And I think to try and move forwards, we need to find a way to find these biomechanical factors that we can change to make meaningful differences in the outcomes that we care about. So hopefully in the long term, if we can send someone home, this is thinking about lower limb biomechanics, we can send someone home with a biofeedback device that would make meaningful changes to their joint loads or their forces, I think we'll be on the right track there, because we can't hook up people to EMG and have very fancy EMG modeling, you know, to have long-term changes to people.
Thank you, Scott. Anyone else wants to make a final remark? Jenny, go ahead.
I was just going to support Marcus's comment about measurement. One of the things that appeals to me about a lower limb exercise, the fact that it will quantify, you know, I want sensors on it. I want it to be giving me information, not just providing assistance. It will give us, you know, to me, that has changed my understanding of how I think about people walking, both healthy people and people with disability. And so I think the notion of measuring, you know, thinking of robotics from that point of view will again be useful.
Okay, thank you. Well, on that note, let's close this. It's already 6:10. Thank you very much to all of you, to all the speakers, to all the attendees here and online. Thank you to the panel members. I hope it was informative, interesting. It certainly was for me. And yeah, I hope we've learned something today and we can move on from here, collaborating and doing the right stuff for the patients. Thank you very much. And yeah, we will close the Zoom now and I'll see you around. Thank you.